If you haven't already, settle in. The day is over. There's nothing you need to do tonight that won't still be there in the morning, and the only useful thing happening in the next few hours is rest. Pull the blanket up if you haven't, let your shoulders drop, soften your face, let the day go where days go. You won't need to remember any of what follows. That's the actual arrangement of these recordings. If you fall asleep 2 minutes in, the story keeps telling itself, and it'll be here when you come back. If you wake up later and have lost the thread, that's also fine. Nothing on the other side of these hours depends on you holding on to anything. The story tonight is about the Internet. Specifically, about how the Internet actually works. The strange thing about the Internet, and you may have noticed this, is that most people who use it every day have essentially no idea what's happening when they use it. They type something into a small bar at the top of a screen, or they tap an icon on a phone, and a thing happens that satisfies them and they go on with their lives. Underneath that surface, an enormous amount of machinery is doing something extremely complicated, and almost nobody who uses the machinery is taught what it's doing. That's what tonight is for. Not to make you a network engineer or to fill your head with acronyms or to give you a quiz at the end. Just to walk you slowly and gently through the strange and quiet machine that has been sitting under your screens this whole time. By the time the story ends, you will, in some real sense, understand how the Internet works, even if you fell asleep most of the way through. Even if you don't remember any of the names or the years or the specific words. Something will have settled somewhere in the back of your mind, where understanding lives, and you'll know more than you did when you started. That's the promise of the title. We're going to actually do this thing. One small thing before we begin, and then I'll stop talking about anything except the story. If you'd like a voice like this in the dark, on other nights, other long, quiet things to drift to tap subscribe now, before you forget. And if you feel like it, leave a comment with where you're listening from. People do, and it turns out there's something quietly nice about scrolling through later and seeing a few hundred other people in a few hundred different rooms, all settling in for the same long night. No pressure on either one, just if you want to. Then we can settle in for real. And I won't ask you for anything else tonight. The story we're about to tell begins the way a lot of stories about important things begin, in a kind of quiet worry about something terrible happening. The year is 1960. The place is a research building outside Los Angeles, and a young engineer named Paul Baran is trying to figure out whether the United States can still talk to itself the day after Moscow drops a hydrogen bomb on Washington. Chapter 1: A network that could survive being attacked. The young engineer was 34 years old. His name was Paul Baran. He had been born in Poland, brought to the United States as a small child, and trained as an electrical engineer. By 1960, he was working at the RAND Corporation, a think tank in Santa Monica, California, that had been founded after the Second World War to study problems that the United States military wanted answered. RAND employees did mathematics, wrote reports, and tried to think about uncomfortable questions that most people preferred not to think about. The most uncomfortable of these questions in 1960 was what would happen to the United States if there were a nuclear war. The question Buran was asked to study was specific. If the Soviet Union launched a nuclear strike against the United States, would the country still be able to coordinate a response? Would the president still be able to talk to his commanders? Would the commanders be able to talk to each other? The communications networks that existed at the time, Buran realized, were not designed to survive that kind of damage. They were telephone networks, and telephone networks in 1960 had a particular structure. They were hierarchical. Calls between distant cities were routed through a small number of large central switching offices. If you destroyed the right 10 or 20 buildings in the country, the long-distance phone network would no longer work. The United States would, in a real sense, go quiet at the worst possible moment. Buran began to think about whether you could design a communications network that wouldn't have this problem. A network where any one piece could be destroyed and the rest would keep working. A network without a center. The structure he eventually proposed was something he called a distributed network. The idea was that, instead of a few large central exchanges, the network would be made up of many small nodes, each connected to several other nearby nodes. There would be no center. The connections would form a kind of dense mesh, like the threads of a fisherman's net. If any single node were destroyed, messages could still find their way around the damage by taking a different path through the mesh. The network would degrade slowly as it was damaged, rather than collapsing all at once. There was a problem with this idea, though. The telephone network worked in a particular way that didn't fit a mesh structure. When you made a phone call in 1960, the network reserved an actual physical path between you and the person you were calling. A continuous electrical circuit that stayed open for the entire duration of the call. This way of working was called circuit switching, and it required that the network know, in advance, the whole path the call would take. In a mesh network with many possible paths, the network would have a hard time setting up a single fixed circuit, especially if pieces of the network were being destroyed in the middle of calls. What Buran proposed instead was something different. Instead of sending each conversation along a fixed circuit, the message itself would be broken into small pieces. Each piece, he imagined, would be put into a kind of envelope with the destination address written on it. Each envelope would be released into the network on its own. Each envelope would, at each step, be passed from one node to the next, with each node looking at the address and making a small decision about which neighboring node would be the best next stop. The envelopes would in effect find their own way through the mesh, with no overall plan. When all of the envelopes arrived at the destination, they would be reassembled into the original message. This was a strange idea. It seemed wasteful. A message that could have been sent along a single path was instead being chopped up and scattered across many paths. It also seemed unreliable. What if some of the envelopes got lost? What if they arrived out of order? The network would have to do extra work to handle these problems. But the idea had two enormous advantages, which Buran spent a great deal of time explaining. The first was that, if one node went down, only the envelopes that happened to be passing through that node at that exact moment would be lost. Everything else would just route around the damage. The second was that the network could carry many different conversations at the same time without any of them interfering with each other. Each envelope was an independent thing, going its own way, sharing the same wires with all the other envelopes. Baran wrote up his proposal in a series of reports for RAND, 11 of them in total, published between 1960 and 1964. The reports were detailed and careful. They described the mathematics of how the network would work. They explained how the addressing would be done. They proposed designs for the hardware. They estimated the costs. The reports went nowhere, at first. The military people who read them were polite but did not act on them. The phone company, AT&T, which Baran had hoped might build the kind of network he was describing, was not interested. AT&T's engineers, when Baran presented the proposal to them, told him politely that it would not work. The telephone system they had built was a careful and expensive thing, and the idea of replacing it with a wild mesh of independent nodes where messages would be chopped into pieces and reassembled struck them as essentially a fantasy. One AT&T executive, in a meeting with Baran, is said to have remarked that the young engineer simply did not understand how telephones worked. Baran went back to RAND. The proposal sat on shelves. Years went. What Baran did not know in the early 60s was that another engineer working independently on the other side of the Atlantic had arrived at almost exactly the same idea. His name was Donald Davies. He was British, a few years older than Baran, and he worked at the National Physical Laboratory in the suburbs of London. Davies had been thinking about the future of computer networks, not about nuclear, but the problems he was trying to solve had led him to the same place. Like Baran, he had concluded that the right way to send data between computers was to break the data into small pieces, send each piece independently, and reassemble them at the other end. Davies in 1965 gave the small pieces a name. He called them packets. The word came from the everyday English usage, in which a packet is a small parcel that contains something. The name was so plain and clear that it stuck. The whole idea, from then on, was called packet switching, in contrast to the circuit switching of the telephone network. By 1966, when Baran and Davies finally heard about each other's work and exchanged friendly letters, the two of them had laid out, between them, the fundamental design of what would become the Internet. There would be no center. The network would be a mesh of nodes. Messages would be broken into packets. Each packet would carry its destination address. Each node would forward each packet toward its destination, making its own small decision about which neighbor to send it to. The network would route around damage. It would carry many conversations at once. What was missing in 1966 was anyone who would actually build such a network. That would come from a different source entirely. It would come from a small group of researchers funded by the same United States military that had originally asked Baran the question about nuclear war, who were getting ready to plug 4 computers together and see what happened. Chapter 2, The First Message. The agency that built the first packet-switched network was the Advanced Research Projects Agency, which was a research office inside the United States Department of Defense. The agency had been founded in 1958, the year after the Soviet Union launched the satellite Sputnik, with the goal of making sure the United States was never surprised again by some other country's technology. It funded research at universities and at private laboratories. It had a small staff, almost no equipment of its own, and an unusual amount of money to give away to interesting people. In the late 1960s, the office that handled computer research at the agency was run by a man named Robert Taylor, who would later go on to start Xerox PARC, the research lab in Palo Alto that invented many of the ideas behind the personal computer. Taylor's office in the Pentagon contained, at the time, 3 different computer terminals, each connected to a different computer at a different university. To use any of the 3 computers, Taylor had to sit down in front of the corresponding terminal. He could not easily move information from one to another. He could not, sitting at the terminal connected to the computer at MIT, send a message to the computer at Berkeley. Taylor was bothered by this. He thought it was absurd, in a small but real way, that the 3 computers his agency was funding could not talk to each other. He went to his boss, a man named Charles Hertzfeld, and asked for $1 million to start a project that would connect the computers his agency funded into a single network. Hertzfeld, by Taylor's later account, gave him the $1 million on the spot. The project would build a network based on Baran and Davies's ideas. It would be a packet-switched network, with multiple paths between any 2 nodes. It would be called the ARPANET, after the agency that was funding it. The contract to design and build the network was given in 1968 to a small consulting firm in Cambridge, Massachusetts, called Bolt, Beranek and Newman, or Bean for short. Bean had a few hundred employees, a particular reputation for clever engineering, and a workforce that overlapped heavily with the computer science departments of MIT and Harvard. The man at Beban who led the technical work was named Frank Hart, and the team he assembled to build the network's first nodes worked through 1968 and most of 1969 in a relentless series of late nights. The first nodes were specialized computers, called Interface Message Processors, or IMPs. Each IMP was about the size of a refrigerator. Each one was designed to connect one of the host computers at a university to the long-distance telephone lines that would carry packets to and from the other nodes in the network. The IMPs were, in essence, the first router. Their entire job was to receive packets from one direction, look at the address on each packet, and send it out in another direction toward its destination. The first 4 nodes were installed at 4 universities on the West Coast and the Southwest. The first was at the University of California at Los Angeles, which took delivery of its IMP on Labor Day weekend in 1969. The second was at the Stanford Research Institute in Menlo Park, California, about a 400-mile drive up the coast. The third was at the University of California at Santa Barbara. The fourth was at the University of Utah in Salt Lake City. The 4 nodes were connected by leased telephone lines that ran at a speed of 50,000 bits per second, which was, in 1969, an extraordinary amount. Today, by comparison, a typical home internet connection runs at about 10,000 times that speed. The first message was sent on the evening of October 29, 1969. The man who sent it was a graduate student at UCLA named Charlie Klein. He was 21 years old. His supervisor was a computer science professor named Leonard Kleinrock, who had been one of the early theoretical thinkers about packet networks. Klein was sitting in front of a teletype terminal at UCLA. On the other end of the leased phone line at Stanford Research Institute was a programmer who had agreed to watch the receiving terminal. The two were also connected by a separate telephone line, the normal voice kind, so that they could talk to each other while they tested the network. The plan was to send the word login, which was the command the Stanford computer would expect in order to start a session. Klein started typing. He typed the letter L. Over the phone, he asked the man at Stanford if he had seen anything. The Stanford man said yes, he had seen an L. Klein typed the letter O. He asked again. The Stanford man said he had seen the O. Klein typed the letter G. The system at Stanford crashed. The first message ever sent across the network that would become the Internet was therefore 2 letters long. The intended message had been login. The actual message had been low. It was by accident a slightly mystical greeting, the kind of word that might have come from a religious text. Behold, lo, Klein rebooted the system at Stanford, and an hour or so later the full message went through. The story of the first message is told, now in computer history books, with the gentle humor of all stories where something important goes wrong on its first try. But the message itself was real. 2 letters had traveled, in the form of packets, from a computer in Los Angeles through an interface message processor in Los Angeles, across a leased phone line to an interface message processor in Menlo Park, and into a computer at Stanford. The fact that the message was incomplete didn't change what had happened underneath. The packets had moved. The network had worked. The first node had spoken to the second node. The dream that Paul Baron had written about in his Rand reports, almost a decade earlier, had taken its first small breath. There was, in those early years at Ookla and the other ARPANET sites, a particular working culture that is worth pausing on, because it shaped almost everything that came after. The graduate students who worked on the network were left mostly to themselves. The professors who supervised them were interested but not closely involved. Nobody from the funding agency was telling them, day by day, exactly what to do. The students were figuring out as they went how the network should actually work. One of those students was a young man named Steve Crocker, who was a graduate student at UCLA and who had been in the room when the first message was sent. Crocker had been assigned, along with a small group of his fellow students, to figure out the higher-level protocols that the network would use. The interface message processors handled the packets at a low level, but the host computers needed to know how to do useful things with the packets they sent and received. How would they identify each other? How would they request specific resources? How would they log in? Crocker, in April of 1969, before the first node was even installed, sat down at a desk in the bathroom of his shared apartment, because he didn't want to wake his roommate, and wrote up some preliminary notes about how he thought the protocols should work. He titled the document a request for comments, because he was worried that if he gave it a more authoritative-sounding title, the other graduate students at other universities would feel that they had to defer to it, when what he actually wanted was for them to argue with him and improve the ideas. The request for comments was numbered 1. He sent it out by mail. The convention that Crocker started, of writing technical proposals as requests for comments, became the standard way the Internet's engineers communicated with each other for decades. The documents are still called RFCs. They are still numbered sequentially. There are now over 9,000 of them. They cover everything from the most fundamental protocols to small details of how particular kinds of messages should be formatted. Many of them are technical and dry. A few of them are jokes, including one published every April 1st that proposes carrier pigeons as a way of carrying internet traffic. The whole library of RFCs is publicly available, free, on the internet. Anyone in the world who wants to understand exactly how some piece of the network works can look up the corresponding RFC and read it. The tradition of openness that Crocker started in a bathroom in 1969 because he didn't want to wake his roommate is one of the reasons the internet became what it became. By the end of 1969, all 4 of the original nodes were online. By 1971, there were 15 nodes. By 1973, the network reached across the Atlantic, with a node at University College London and another at a research facility in Norway. By the end of the 70s, the ARPANET had grown to several hundred nodes, mostly at universities and research labs, scattered across the United States and a few other countries. The hosts on the network were a strange and varied collection of computers from many different manufacturers, running many different operating systems. The network worked because each host was connected to an IMP, and the IMPs all understood the same protocols for sending and receiving packets, even when the hosts themselves did not. What the ARPANET demonstrated, more than anything else, was that the idea of a packet-switched network could be made to work in practice. The IMPs did indeed route packets around damaged nodes. The network did indeed support many conversations at the same time. The structure that Baran and Davies had imagined on paper was, by the mid-70s, a real thing that real people used to send messages to each other every day. Researchers at universities began to depend on it. Students learned to log into computers at other schools through it. The first email systems were written on top of it. The first online discussion groups appeared. The ARPANET was the seed. What grew out of it over the next decade was something much larger. It was something that needed a new name and a new way for many different networks to talk to each other, and a new design that no single agency or company would own. The men who would design that new thing were already working on it. One of them was a soft-spoken Stanford professor named Vint Cerf, and the other was a soft-spoken DARPA program manager named Bob Kahn. And what they were about to invent would still be running the Internet 50 years later. Chapter 3: The Two Men Who Designed the Language. Vinton Cerf was 29 years old in 1972, the year he began the work that would define the Internet for the rest of his life. He had been born in New Haven, Connecticut, raised in California, and trained as a computer scientist at Stanford. He was, by every account, a courteous and methodical person. He had a habit of wearing 3-piece suits, which set him apart from the engineers around him who mostly wore jeans. He had a beard which he kept neatly trimmed. He worked in the early 70s as an assistant professor at Stanford, where he taught computer science and ran the research group that was responsible for one of the ARPANET nodes. Robert Kahn was a few years old. He had been born in Brooklyn, trained at Princeton, and worked for a few years at AT&T before joining Bibbin, where he had been one of the engineers who designed the original interface message processors. In 1972, he had left Bibbin to take a job at the Advanced Research Projects Agency, where he was now a program manager. He was tall, intense, and had a particular gift for explaining technical ideas in simple language. He and Cerf had met at the University of California at Los Angeles in 1969 during the early testing of the first ARPANET nodes, and they had become friends. The problem that Kahn had been thinking about in the early 70s was that the ARPANET was only one kind of network. The agency, by 1972, was funding research on several other kinds. There was a radio-based network called the Packet Radio Network, which used radio transmitters mounted on trucks to send packets between mobile users. There was a satellite-based network called the Satellite Network, which used a satellite over the Atlantic to connect researchers in Europe and the United States. Each of these networks had been designed independently. Each used a different way of breaking messages into packets, of addressing them, of forwarding them. They were, in essence, 3 different languages spoken by 3 different networks. They could not talk to each other. What Kahn wanted was a way to connect these different networks together so that a message could travel from one to another. A packet that started on a host on the ARPANET, for example, might need to travel out to a host on the Packet Radio Network, and then perhaps onward to a host on the Satellite Network. For this to work, the different networks would need to agree on a common length, a set of rules that everyone followed, so that packets could pass between them without getting confused. In 1973, Kahn asked Cerf, his old friend from Ookla, to help him design this common language. The two of them spent several months that year working out the design, mostly in long conversations at hotels and conference rooms, sometimes sketching diagrams on napkins. They produced, in May of 1974, a paper that has since become one of the most influential documents in the history of computing. It was called A Protocol for Packet Network Intercommunication. The protocol it described would, after several years of refinement, come to be known as TCP/IP. The 2 letters, TCP and IP, stood for 2 related protocols that worked together. The IP, which stood for Internet Protocol, handled the actual routing of packets from one network to another. Every packet under IP would carry a destination address in a particular format. Every router, when it received a packet, would look at that address and forward the packet toward the destination. The format of the address was a number with 4 parts, separated by dots. A typical address might be something like 172.16.254.1. The 4 parts together identified one specific machine on one specific network, anywhere in the world. The system had been designed to allow for over 4 billion possible addresses, which seemed in 1974 like more addresses than the world could ever possibly need. The TCP, which stood for Transmission Control Protocol, handled a different problem. Packets, when they traveled across the network, could arrive out of order, because each packet found its own way through the network and faster paths sometimes overtook slower ones. Packets could also be lost if a router along the way became overloaded and had to drop some of them, or if a connection failed in the middle of a transmission. The TCP handled both of these problems. At the sending end, it numbered the packets in order before they were released into the network. At the receiving end, it sorted the arriving packets by number and put them back in the right sequence. It also kept track of which packets had arrived, and if any were missing, it asked the sender to resend. The TCP, in effect, made the network look reliable to the programs that used it, even though the network itself was not reliable. The combination of these two protocols turned out to be enormously flexible. Any network that was willing to implement IP could connect to any other network that did the same. The addressing was universal. The routing was distributed. Each network could, internally, use whatever technology it wanted, whether that was telephone lines or radio waves or satellite beams. As long as it spoke IP at its edges, it could be part of the larger system. The larger system was called, around this time, the Internet, with a capital line short for the Internetwork, which was the network of networks. Cerf and Kahn refined the design through the mid and late 70s. The first working implementation of TCP/IP was running between a small number of nodes by 1977. Over the next several years, the protocols were tested, debugged, and gradually improved. The final version, the one that would become a global standard, was settled in 1981. The Defense Department, which had been funding all of this work, then made a decision that would change the world. The Defense Department announced that, on January 1, every computer on the ARPANET would be required to switch from the old way of communicating to the new TCP/IP protocols. The switch would happen on a single day. After that day, any computer that wanted to be on the network would have to speak TCP/IP. There would be no going back. The date is now sometimes called Flag Day, in the way that important dates in the history of a country are sometimes called. On the morning of January 1, 1983, the engineers at the various ARPANET sites flipped their computers from the old protocol to TCP/IP. Some of the sites had trouble. Some of them stayed offline for hours while engineers debugged their configurations. By the end of the day, most of the network was running on the new protocols. By the end of the month, almost all of it, the Internet, in essentially the form it has today, had been born. What Cerf and Kahn had designed, in their hotel rooms and on their napkins in 1973, would still be running every packet of Internet traffic in the world 50 years later. The 4 dotted numbers they invented would still be on every packet. The retransmission logic of TCP would still be quietly resending lost packets in the background of every video call and every web page load and every email. The system would expand to billions of users and trillions of devices in ways that nobody in 1974 had quite imagined, but the underlying design would not need to change. The protocol that 2 friends had sketched on napkins would still, 50 years on, be exactly the protocol that the world's networks all spoke. Cerf, by the way, would later spend much of his career at Google, where he was given the official title of Chief Internet Evangelist, and where he would travel the world giving talks about the Internet's history and future. Kahn would go on to found a research organization that worked on what he called the digital object architecture. The 2 of them would remain friends, and would receive, over the years, almost every major award that computer science has to give. They would, in interviews, tend to deflect credit toward the other person, which is the kind of thing close friends do when both of them are unusually decent men. Chapter 4: The Phone Book of the World. There is a problem that Cerf and Kahn's protocols did not solve, which is that human beings do not remember numbers very well. The 4 dotted addresses that identify every computer on the Internet, the ones that look like 172.16.254.1, are perfectly fine for computers to use, but they are difficult to remember. They are also difficult to write down. They change sometimes when a computer moves or when its network is reorganized. They have no meaning to a person. If the only way to refer to a website were by its number, the Internet as we know it would not function. What people use instead are names. The name of a website is something like wikipedia.org or gmail.com or bbc.co.uk. The names are easy to remember. They suggest, in their structure, what the website is about. They stay the same even when the underlying machines change. They are what we type into our browsers and what we say to each other when we recommend a place to visit on the Internet. But the network itself doesn't understand names. The network only understands numbers. When you type a name into your browser, the browser has to translate that name into a number before it can do anything else. The system that performs this translation, quietly and invisibly, every time you visit a website or send an email or open an app, is called the Domain Name System, or DNS. It is, in essence, the phone book of the Internet, and it is one of the strangest and most quietly impressive pieces of engineering in the entire system. For the first many years of the network's life, the translation between names and numbers was handled by a very simple method. There was a single file, called hosts.txt, which was a plain text document that listed every computer on the network and its corresponding. The file was maintained by a woman named Elizabeth Feinler, who worked at the Stanford Research Institute, where she ran what was called the Network Information Center. When a new computer joined the network, someone would call Feinler's office or send her an email, and her staff would add a line to the file. Periodically, every computer on the network would download a fresh copy of the file from a central server. This worked for a while, when the network was small. By the early 80s, however, the network was no longer small. It had several hundred hosts, and was growing. The hosts.txt file was getting too big. The central server that distributed it was getting overloaded. The system was beginning to fail. Something better was needed. The man who designed the something better was a computer scientist at the University of Southern California named Paul Macapetris. He was in his early 30s. He had been working at the Information Sciences Institute, which was a research center associated with the university that did much of the engineering work for the Internet in those years. He had been asked by his supervisors to figure out a replacement for hosts.txt. The replacement needed to be able to handle many more names than the original file. It needed to be updated quickly when new names were added. It needed to be distributed so that no single central server would have to handle all the queries. It needed, in the spirit of the original network design, to have no sense. Macapetris worked on the design for most of 1983. The system he proposed had a particular shape, which is worth describing carefully, because it is the same shape the system still has today. He proposed that names should be arranged hierarchically in a kind of tree. At the top of the tree, there would be what he called top-level domains. These would be a small number of categories like COM for commercial entities or org for non-profit organizations or for educational institutions, or for government agencies. Each country in the world would also have a top-level domain of 2 letters, like UK for the United Kingdom, or for France, or JP for Japan. The top-level domains would all live at the root of the tree. Under each top-level domain there would be a second level of names. Under com, for example, there would be names like google.com and amazon.com and apple.com. Under uk there would be subcategories like co.uk and act.uk, and then under those there would be specific names. The structure could keep going. Names could have as many parts as needed, separated by dots, with each part being more specific as you moved from right to left. The genius of Makapetrus's design was in how the translation between names and numbers would actually be performed. He proposed that there would be no single computer that knew the translations for every name. Instead, the work would be divided up. There would be a small number of root servers which knew which other servers were responsible for each top-level domain. The root servers would not know the answers themselves. They would just know who to ask. Beneath the root servers, there would be servers responsible for each top-level domain. These would know which servers were responsible for each second-level name. They would not know the answers either. They would also just know who to ask. Beneath those, there would be servers responsible for individual companies and organizations. These would actually know the answers, but only for the names within their own organization. Google's servers would know the numbers for the various computers within Google. The university's servers would know the numbers for the various computers within the university. When your browser needs to translate a name into a number, it makes a sequence of queries. It asks a root server, which directs it to the appropriate top-level domain server, which directs it to the appropriate organizational server, which finally gives the answer. The whole process takes a fraction of a second, and is repeated, more or less, every time you visit a new website or send an email to a new. Makapetrus published the design in 1983 in a technical document called a Request for Comments, which was the format used by the Internet's engineers for proposing new protocols. The document was numbered RFC 882. The system it described, the domain name system, was deployed gradually over the next few years, and by the late 80s had completely replaced hosts.txt. The domain name system is, today, one of the most reliable pieces of distributed software in human history. Every time you visit a website, somewhere around the world, a small set of queries is being made through the DNS hierarchy. The total number of queries handled by the system every day is something like 100 billion. Almost all of them succeed. Almost all of them complete in less time than it takes you to read this sentence. There are 13 root servers, in the technical sense, although each of the 13 is actually a cluster of many machines spread around the world. The root servers are operated by 12 different organizations, including the United States Department of Defense, several universities, and a few non-profit foundations. They have been running in some form since 1985. They have never, all at once, gone down. The shape of names that Makapetrus drew on paper in 1983, with com and org and edu at the top and individual names beneath them, is still the shape of names on the Internet today. There is one more person who deserves to be mentioned here, although his contribution was less specific than Macapetris, and his name is less remembered. His name was John Postel. He was a graduate school classmate of Vint Cerf's at UCLA in the late 60s. He stayed close to the engineering work of the Internet for the rest of his life. He worked for many years at the Information Sciences Institute in Southern California, and he was by general acknowledgement the person who quietly kept the Internet's various pieces of paperwork in order through the 70s and 80s. He maintained the lists of IP address assignments. He kept track of which numbers had been given to which organizations. He published the protocol documents. Postel had a long beard and wore sandals and was, by every account, a deeply gentle and unassuming man. He was sometimes called the God of Names because of his stewardship over the lists that allocated names and numbers on the Internet. He did this work for most of his career almost single-handedly with very little budget and almost no formal authority. He died of complications from heart surgery in 1998 at the age of 55. The functions he had performed alone were taken over, after his death, by a non-profit organization called the Internet Corporation for Assigned Names and Numbers, or ICANN, which now has hundreds of employees and a multi-million-dollar budget, and which is, in essence, his ongoing legacy. Chapter 5: The Wires You Cannot See. Up to this point, we have mostly been talking about the Internet as an idea, as a set of protocols, as agreements between computers about how to address and forward small pieces of data. But the Internet is also, very importantly, a physical thing. It exists in the world. It is made of wires and switches and antennas and concrete buildings and fiber optic cables, and undersea trenches, and millions of objects that have actual weight and take up actual space. To understand how the Internet works, it helps to spend some time thinking about what the Internet actually is, in terms of the physical material it occupies. The largest pieces of the physical Internet are the undersea cables. These are the cables that carry traffic between continents. There are, as of these recordings, about 500 of them in active service laid across the floors of the world's oceans. The cables connect, for example, the east coast of the United States to Europe and the west coast to Japan, and South America to Africa, and Australia to almost everywhere. Most of the traffic that crosses the world's oceans, including almost every video call between continents and almost every web page loaded from a foreign country, travels through these cables. Satellites carry some traffic, but they are much slower and have much less capacity, and the undersea cables are where the real work is done. A typical undersea cable is about the diameter of a garden hose, although the older ones were thicker and some of the newer ones are thinner. The cable contains at its core a small bundle of fiber optic strands. Each strand is a thin piece of glass, slightly thicker than a human hair, through which pulses of light can be sent. The pulses, each lasting a tiny fraction of a second, represent the ones and zeros of digital data. A single fiber optic strand can carry an enormous amount of data, because the light pulses can be sent very, very fast, and because many different colors of light can be sent through the same strand at the same time without interfering with each other. A single modern cable, with several dozen fibers inside it, can carry the digital equivalent of millions of phone calls at once. The cables are laid by special ships, called cable ships, which are owned by a small number of specialized companies. The work of laying a cable across an ocean is slow and careful. The ship steams across the planned route at a few miles per hour, paying out the cable from a large reel on the deck. The cable descends into the water behind the ship and settles onto the ocean floor below. The ship may have to make small adjustments to avoid underwater mountains or known shipwrecks. A long cable, like the ones that cross the Pacific, can take months to lay. Once the cable is in place, it is mostly out of sight. The deepest parts of the ocean floor, where most of the cables run, are completely dark and almost completely still. A cable that has been laid in the deep ocean might lie there for 30 years without being touched, while trillions of bits of human communication pulse through it every second. The cables are occasionally damaged, usually by fishing trawlers in shallower water or by ships dropping anchors, or in rare cases by undersea landslides or earthquakes. When a cable is damaged, the cable ships are dispatched to find the break, lift the broken ends up to the surface, splice them back together, and lower them back down. This is, by all accounts, slow and difficult work. A typical major undersea cable costs a few $100 million to build and lay, and is owned in most cases by a consortium of several companies, including telecommunications companies and the large internet firms that depend on the traffic the cable carries. Google, Facebook, Amazon, and Microsoft are all, by the early 2020s, partial owners or operators of multiple major cables. The Internet, despite its origins as a government-funded research project, is now mostly a private infrastructure owned and operated by a relatively small number of large corporations. The cables that come ashore at the edges of continents land at specific places, called cable landing stations. These are usually small concrete buildings near beaches in slightly out-of-the-way locations. There is one, for example, near a village in Cornwall, England. That has been a major landing station for transatlantic cables for over 150 years, going back to the first telegraph cables in the 19th century. There is another near Manasquan, New Jersey. There are several in places like Hong Kong, and Lagos, Nigeria, and Mumbai, India. The cable landing stations are usually not marked. They look like ordinary small industrial buildings. The cables that emerge from them go underground, are buried in trenches, and run inland to data centers and exchange points in major cities. The next layer of the physical internet is the long-distance terrestrial cables. These are the cables that run between major cities within a country. Some of them are buried along highways. Some of them are buried along railroad tracks. Some of them follow the routes of older infrastructure, like the rights-of-way of 19th century telegraph lines, or oil pipelines, or canals. The geography of the long-distance cables tends to follow the geography of older infrastructure, because those rights-of-way are already legally established and already free of obstacles. The same paths that carried telegraph wires in 1860 often carry fiber optic cables today. The places where the long-distance cables meet in major cities are called Internet Exchange Points, or IXPs. An exchange point is, in physical terms, a large building, usually in a downtown area, where many different network operators have brought their cables together. Inside the building, the cables are connected to large pieces of equipment called switches, which let the operators exchange traffic with each other. If you live in London and you visit a website hosted in Frankfurt, the packets carrying that website to your home almost certainly pass through one or more major exchange points in their journey. The most famous exchange point in the world by some measures is one in Frankfurt itself, called DE6, which handles more traffic than almost any other place on Earth. Underneath all of this, at the very bottom of the physical layer, are the wires and signals that reach individual homes and businesses. This is sometimes called the last mile of the Internet. The last mile is usually the slowest part of the system. It is also the most expensive part of the system to build, because it requires running cables to every individual building, rather than just between major facilities. The last mile in most parts of the world is run by local Internet service providers, or ISPs, who have contracts with the building owners and the local governments to install and maintain the connections. The technology used for the last mile varies. In some places, it is fiber optic cable, the same kind of cable used in the long-distance and undersea systems. In other places, it is older copper cable originally installed for telephone service decades ago, with newer equipment at each end to send digital signals over it. In other places, it is coaxial cable, originally installed for cable television. In other places, especially in apartment buildings, it is a mix. In rural areas, it is sometimes wireless, with antennas on towers that send signals to receivers on the sides of houses. In a few places, it is delivered by satellites in low Earth orbit, which is a recent development. The point of describing all of this is that the Internet, when you type a name into your browser, is not just an idea. It is a physical chain of objects. The signals leave your phone or your laptop, travel through your home's wiring to a small box called a router or a modem, travel from there through the local ISP's network of cables, travel from there through one or more long-distance cables to a major exchange point, possibly travel from there through an undersea cable to another continent, travel through more cables on the other side, and arrive, finally, at a data center where the website you are visiting is hosted. The whole journey for a small request takes about 1/10 of a second. Each of the thousands of miles your packets travel is a real piece of glass or copper or fiber somewhere in the world that someone laid in a trench at some point. The Internet is invisible to you, but it is not invisible. It is just bare. Chapter 6: Strangers Forwarding Packets for Strangers. The packets, having left your device, now have to find their way through this physical network to wherever they are going. This is the work of routing, and it is one of the more surprising parts of how the Internet works, because of how the decisions are actually made. The Internet, as a whole, is not made up of a single network. It is made up of tens of thousands of smaller networks, each operated independently by a different organization. Each of these smaller networks is called an autonomous system, and each one has a number that identifies it. Your home Internet service provider is one autonomous system. The university or company that hosts a particular website is another. The large transit networks that carry traffic between continents are others. There are, as of these recordings, about 100,000 autonomous systems in the world. Each autonomous system is in charge of some specific range of IP addresses. Your internet service provider, for example, owns a particular block of numbers, and any device that connects through them gets an address from within that block. A large company that runs many servers might own its own block. The blocks are assigned originally by the regional Internet registries, which are 5 organizations around the world that handle the allocation of IP addresses for different parts of the planet. The regional registries get their allocations from the Internet Assigned Numbers Authority, which is the modern continuation of the work that Jon Postel did alone for many years. When a packet leaves your device with a destination address on it, the first thing that happens is that your home router looks at the address and decides where to send the packet next. Your home router is connected to your internet service provider's network. It doesn't know how to get to the destination directly, but it knows that for any address it doesn't recognize, the right thing to do is to hand the packet up to its provider. So it does. The packet goes out across the last mile cable to the provider's network. Inside the provider's network, the packet meets a larger router which has more information. This router knows the layout of the provider's network in detail. It knows where each of the provider's customers is connected. If the destination address belongs to one of the provider's other customers, the router can send the packet directly to them. If not, the router has to send the packet onward to one of the provider's connections with other autonomous systems. The question of which connection to use is where things get interesting. The router has to choose, for each packet, which neighboring autonomous system is the best one to forward the packet to. To make this choice, the router consults a kind of internal map called a routing table, which lists, for each range of destination addresses, which neighbor to send the packets to. The routing table is enormous. A typical router on a large network has a table with several 100,000 entries, one for each block of addresses on the Internet. The way these routing tables are built and updated across all the autonomous systems of the world is by a protocol called the Border Gateway Protocol, or BGP. BGP is, in some sense, the system by which the Internet talks to itself about its own structure. Each autonomous system using BGP announces to its neighbors which ranges of addresses it can reach. The neighbors take these announcements and pass them along to their neighbors, adding their own information about who reached the announcement. Over the course of a few minutes, the announcements propagate across the entire world. Every router on every network ends up with a more or less complete picture of which autonomous systems can reach which addresses, and how many hops away each one is. When a router has to decide where to forward a packet, it looks at the routing table built from these announcements and chooses the path by some combination of measurements is the shortest or the cheapest or the least congested. The packet then goes to that neighbor. The neighbor does the same thing, choosing the best onward path from its own routing table. The packet hops, autonomous system by autonomous system, across the Internet, until it arrives at the autonomous system that owns the destination address, which then delivers it to the specific machine. There is a strange and quiet feature of this system that is worth pausing on. The system depends on every autonomous system telling the truth about which addresses it can reach. There is no central authority that verifies these announcements. When one network announces through BGP that it can reach a particular range of addresses, the other networks of the world just believe it. They update their routing tables accordingly. They start sending traffic that way. This works most of the time because most of the people who operate networks are honest, or at least are not actively interested in misrouting other people's traffic. But the system is also vulnerable. If a network operator, by mistake or on purpose, announces that it can reach addresses it cannot actually reach, traffic that should have gone elsewhere will be sent to it instead. This happens in small ways fairly often. It has happened in large ways several times in the history of the Internet. The first famous example happened on the morning of April 25, 1997. A small Internet service provider in McLean, Virginia, called My Network Services, which had the autonomous system number 7007, made a configuration mistake. The mistake caused My's routers to announce to all of its neighbors that My itself could reach every block of Internet addresses in the world by the shortest possible path. The announcement was, of course, untrue. My was a small company with a small network. But the other autonomous systems on the Internet had no way to verify the claim, and so they accepted the announcement and updated their routing tables. For about 2 hours on that April morning, a substantial portion of the world's Internet traffic was being routed through My's small network in Virginia, where it overwhelmed the company's modest hardware and was mostly dropped. Large parts of the global Internet for those 2 hours were essentially offline. The mistake was eventually noticed. The offending router was disconnected, and the rest of the world's routers slowly recalculated their routes. The incident is still studied in computer science courses as a cautionary example. In 2008, something similar happened with a different cause. The government of Pakistan had decided to block access to a popular video sharing website because of a video it considered offensive. The state-owned telecommunications company in Pakistan attempted to implement the block by announcing internally on its own network that it had a more specific route for the video site's addresses than the real owner did. The route was supposed to direct Pakistani users to a page that said the site was blocked. By accident, however, the Pakistani announcement was not kept internal. It leaked out through Pakistan's upstream provider in Hong Kong into the global BGP system. Within minutes, networks around the world were sending traffic destined for the video site into Pakistan, where it was being dropped. The effect for users in many countries was that the video site appeared to be down. It took the website's operators a few hours to figure out what was happening, contact the relevant network operators, and have the false route withdrawn. During those few hours, almost nobody in the world could watch a video on the affected site. There have been other incidents like these over the years, some accidental, some not. In 2017, a small Russian provider announced routes for parts of several major American banks and financial firms with similar effects. The networking community has developed various technical measures to make these hijacks harder, including a system called Root Origin Authorization that lets address owners cryptographically sign their announcements so that other networks can verify that the announcements are legitimate. The deployment of these measures has been slow and is still ongoing. The deeper truth about the Internet, which becomes visible once you understand how routing works, is that the Internet is, in some real sense, a network built on trust. Every autonomous system trusts its neighbors to tell the truth about which addresses they can reach. Every neighbor trusts the autonomous system on the other side. The whole structure of global packet delivery, the system that moves trillions of pieces of data between continents every day, runs on the assumption that the people who operate the world's networks are mostly going to behave honorably. There is no police force. There is no central authority that can punish a network for misbehaving. There is, in fact, no central authority at all. The system works because, on the whole, it works, and because the small handful of cases in which it doesn't work are corrected, after the fact, by the network operators noticing and talking to each other. This is perhaps the strangest thing about the Internet, and the thing that least gets explained when people describe it. The Internet does not function because some single organization runs it. It functions because tens of thousands of separate organizations, mostly for-profit companies but also universities and government agencies and a few non-profits, agree to follow a shared set of protocols and a shared etiquette of routing. The system is, in its actual operation, a kind of slow consensus among strangers. The strangers are, in most cases, network engineers who have never met each other, who work in different time zones, who speak different languages, and who are nevertheless quietly cooperating every minute of every day to deliver each other's pack. Chapter 7a Document about Documents. By the late 1980s, the Internet in its underlying structure was essentially built. The protocols were settled, the names worked, the routing worked. The physical infrastructure was being laid. What the Internet did not yet have in the 80s was much that an ordinary person would want to do with it. The applications that ran on the Internet in those years were mostly things that engineers and academics used. Electronic mail, file transfer, remote login to other computers. There was no World Wide Web. There were no websites in the sense we now mean the word. There were, in fact, almost no resources that an ordinary user could browse. The man who would change this was named Tim Berners-Lee. He was British, born in London in 1955, the son of two mathematicians who had both worked on one of the first commercial computers in the early 1950s. He had grown up around computers in the way that some children grow up around bookstores. He had studied physics at Oxford, and then, in 1980, had taken a short consulting job at a particle physics research center in Switzerland called CERN. CERN was the European Organization for Nuclear Research, an enormous international laboratory built underground near Geneva, where physicists from many countries collaborated on experiments involving very small particles and very large machines. Berners-Lee, during his short consulting stay at CERN, had built a small program for himself, almost as a personal note-taking system. The program let him store little pieces of information and link them together. If he wrote a note about a particular physicist, and then mentioned a particular experiment that physicist had worked on, the note about the physicist could contain a link to the note about the experiment. Clicking the link would jump to the other note. The program was called Enquire, after a Victorian household encyclopedia called Enquire with In Upon Everything, which had been on the bookshelf at Berners-Lee's childhood home. The Enquire program was small, personal, and did not catch on with anyone but its author. Berners-Lee returned to England at the end of his consulting term. He went back to CERN in 1984, this time as a full employee. By then, he had been thinking, on and off, about how the Enquire idea might be made to work on a larger scale. CERN, at the time, employed thousands of scientists from many different countries, who used many different computers running many different operating systems, and who produced enormous quantities of research notes and papers that were difficult to share or find. The information at CERN was scattered. Different research groups kept different records. Documents lived on different machines in different formats in different places. Finding a particular piece of information often meant emailing several people and being directed to several different file servers. Berners-Lee proposed in March of 1989 a system that would solve this problem. He wrote a short memo to his manager, titled Information Management, a Proposal. The memo described a system in which documents could be stored on any computer on the network, could be given a unique address, and could contain links to other documents on other computers. A scientist could publish a document by putting it on a server. Anyone else, anywhere in the organization, could read the document by typing its address into a small program called a browser. The document could contain links to other documents, and clicking on a link would automatically fetch the linked document from wherever it was stored. His manager wrote a comment on the proposal that has since become famous. The comment, written in the margin of the memo, said, simply, vague but exciting. The manager, who was named Mike Sendall, gave Berners-Lee permission to spend some time working on the idea, but did not give it a formal priority. Berners-Lee worked on it, mostly on the side, through 1989 and into 1990. What Berners-Lee built over the course of about a year was several interconnected pieces of software. The first was a way of formatting documents so that they could contain links, which he called the Hypertext Markup Language, or HTML. HTML was a simple text format. A document in HTML was just a plain text file, with small bits of formatting written in around the text using angle brackets. The angle brackets contained tags which told a reading program where headings and paragraphs and lists should be, and which marked the places where links to other documents began and ended. The format was simple enough that a person could write HTML by hand in a text edit without any special tools. The second piece was a way of specifying the address of a document, which he called the Uniform Resource Locator, or URL. A URL was a string of characters that uniquely identified a particular document on a particular computer somewhere on the Internet. A typical URL might be something like http://info.cern.ch/hypertext/ the document name. The first part, HTTP, identified the protocol that would be used to fetch the document. The second part, info.cern.ch, identified the server. The third part, after the slash, identified the specific document on that server. The third piece was the protocol that would actually be used to fetch documents, which he called the Hypertext Transfer Protocol, or HTTP. HTTP was a very simple set of rules for how a browser could ask a server for a document and how the server would respond. The browser would send a short message that essentially said, "Please give me this document." The server would send back the document, or, if the document didn't exist, a message saying so. There was no negotiation, no authentication, no complexity. The whole protocol was designed to be as simple as possible, so that small servers could implement it easily. The fourth piece was the first browser, which Berners-Lee wrote on his NeXT computer, the high-end machine that Steve Jobs' company had built after Jobs had been pushed out of Apple. The browser was the program that a person would actually use to read documents. It displayed HTML pages on the screen, with the links shown as underlined words. When the user clicked on a link, the browser fetched the linked document and displayed it. The browser was, by all accounts, much more elegant than any other program of its kind would be for several years afterward, partly because Berners-Lee had had the NeXT's unusual graphical environment to work with. The fifth piece was the first server, also running on the NeXT, which held a small collection of documents that described the system and how it worked. The server had a sticker on it that Berners-Lee had written by hand. The sticker said, "This machine is a server. Do not power down." The sticker was a friendly request to the night shift workers at CERN who sometimes powered down idle machines to save to please leave this particular machine running. The sticker has been preserved and is now in a museum. Berners-Lee began calling the system the World Wide Web. The name was descriptive. The system was a network of documents that linked to each other in complex patterns, and a pattern of the links, if you could see it, would look like a web. The first version of the web went live on the internal CERN network in late 1990. By the summer of 1991, Berners-Lee had made the software available to anyone outside CERN who wanted to download it. The most important decision he made in this period was to give the web away. He could have patented the protocols he had invented. He could have charged license fees. He could have built a company around the web and become very wealthy. He chose not to. He believed deeply that the web would only grow into the universal medium he imagined if it were free for anyone to use. He negotiated with CERN to release the web specifications into the public domain. CERN agreed. The protocols, the formats, the source code for the first browser and the first server, all of them, were made freely available to the world in 1993. What followed over the next several years was a kind of explosion that nobody, including Berners-Lee, had quite expected. Other people began to build their own browsers and their own servers and to publish their own documents on the web. The number of websites in the world grew from 1 in 1990 to 10 by 1992 to 130 by 1993 to over 10,000 by 1994 to over 1 million by 1997 to over 1 billion by the late 2020s. The web became the medium through which most of the world's information was published, and through which most of the world's commerce was conducted, and through which most of the world's communication began to take place. Tim Berners-Lee, who had built the whole thing himself, in a year of work at a physics laboratory in Switzerland, was knighted by the Queen of England in 2004. The first website ever made, the one Berners-Lee built on his NeXT computer at CERN, still exists. CERN has restored it to its original location and keeps it running as a small piece of museum history. It is at info.cern.ch, and it is a single page of plain text with a few links written in 1991, describing what the World Wide Web is and how to use it. The links still work. The page still loads in any modern browser in a fraction of a second. The protocols Berners-Lee invented are still the protocols every other website in the world uses. The format he chose for URLs is still the format that every website's address takes. The whole edifice, 35 years on, is still recognizably what one person sketched out in a memo titled vague but exciting. Chapter 8: The Browser That Changed Everything. The web, in its first 2 years, was used mostly by physicists. Berners-Lee's browser ran only on the NEC XT, which almost nobody had. Other early browsers were written by various people, but they were all somewhat awkward, and they all ran only on particular kinds of computers. The web in 1992 and early 1993 was a real thing, but it was a real thing that most of the people in the world could not actually use. The man who changed this was 22 years old in early 1993. His name was Marc Andreessen. He was a computer science student at the University of Illinois at Urbana-Champaign, where he worked as a part-time job at the National Center for Supercomputing Applications, a research center funded by the federal government. He was tall and somewhat shy and was, by his own account, not having a particularly exciting year. He was paid $6.85 an hour. At the Supercomputing Center, Andreessen and a small group of his colleagues had heard about Tim Berners-Lee's web and had decided to build their own browser for it. The browser they wrote was called Mosaic. It had 2 important properties that the existing browsers did not have. The first was that it could run on the kinds of computers that ordinary people actually owned, including the Microsoft Windows machines and the Apple Macintoshes that dominated the consumer market. The second was that it could display images alongside the text of a web page. Earlier browsers had supported only text, with images displayed as separate pop-up windows if at all. Mosaic could put images directly into the page, where they belonged. The combination of these 2 properties was, in retrospect, what made the web into something the world could use. A web page in Mosaic was no longer a page of plain text with a few links. It was a page that could contain photographs, and diagrams, and decorative graphics. It was in essence a printed magazine page that you could click on. For the first time, the web looked like something that an ordinary person might want to read. Mosaic was released free of charge in early 1993. The version for Unix workstations came first. The version for Windows came a few months later in November. The version for the Macintosh came shortly after that. Within months of each release, the number of people downloading Mosaic was doubling every few weeks. The number of websites being created was doubling at a similar pace, because more people had browsers and so more people had a reason to make a page. The web, which had been a quiet experiment among physicists, became, over the course of about 18 months, a thing that people heard about in newspapers and saw demonstrated on television. Andreessen graduated from college in late 1993. He moved to California. He had heard from various contacts in the technology industry that what he had built at the Supercomputing Center was potentially very valuable, and that he should consider starting a company. He met, in early 1994, a man named Jim Clark, who had founded an earlier company called Silicon Graphics, which had been one of the more successful Silicon Valley companies of the 80s. Clark was looking for his next venture. He was impressed by Andreessen and by what Mosaic had done. The two of them, after a few months of conversations, decided to start a company together that would build a better browser and would try to make a commercial business out of the web. The company they founded in April of 1994 was originally called Mosaic Communications, but was forced, after a complaint from the University of Illinois, to change its name. The new name was Netscape Communications. The browser the company built, which was a faster and more polished successor to Mosaic, was called Netscape Navigator. The company hired many of the engineers who had originally worked on Mosaic at the Supercomputing Center, including most of Andressen's old colleagues. Netscape Navigator was released in late 1994. Within a year, Netscape Navigator was being used by something like 90% of the people who used the web. The company grew explosively. In August of 1995, Netscape went public on the stock market in what is now generally considered to have been the moment when the Internet became a commercial reality in the public consciousness. The company's stock price doubled on the first day of trading. Andreessen, who was 24 years old, became, on paper, very wealthy. The cover of Time magazine that year ran a photograph of him sitting barefoot on a throne, looking slightly uncomfortable. The Netscape moment, in retrospect, was the beginning of what came to be called the dot-com era. The years between 1995 and 2000 were a strange period in the history of the Internet, in which a great deal of money was invested in companies that built websites and online services, and many of those companies grew very large very quickly. And many of them also failed very quickly when the market for their stocks collapsed in 2000 and 2001. We will not, in this story, go into the dot-com era in detail, because it is mostly a story about money rather than about how the Internet works. But the dot-com era is the moment when the web became the foundation of most of what people now use the Internet for. Other companies entered the browser market. Microsoft, which had been slow to notice the web, released its own browser called Internet Explorer in 1995. Microsoft made Internet Explorer free and bundled it with the Windows operating system that ran on most of the world's personal computers. Over the course of the late 90s, Internet Explorer displaced Netscape Navigator as the most widely used browser. Netscape, as a company, declined. Andreessen left. The company was bought in 1999 by AOL. The competition between Microsoft and Netscape in the years between 1995 and 1998 was sharp enough that people in the technology industry took to calling it the browser war. The two companies were releasing new versions of their browsers every few months, each version adding new features that the other browser did not yet support. The new features were often incompatible with the corresponding features in the other browser, which meant that website builders had to choose which browser to support, or write their pages twice, once for each. The result was a period of several years in which the experience of using the web depended a great deal on which browser you happened to be using, and during which website incompatibilities were a constant source of frustration for users and developers alike. What gave Microsoft an enormous advantage in this competition was not so much that Internet Explorer was a better browser than Netscape Navigator, although in some respects, by the late 90s, it had become so. The advantage was that Microsoft owned Windows, and Microsoft was including Internet Explorer in every copy of Windows it sold. Most personal computers in the world ran Windows. Most of those computers, after about 1996, came with Internet Explorer already installed. Most users, when they took a new computer out of the box, used the browser that was already there. The fact that you could download a different browser, free, from the Internet, did not matter for most people, because the browser they already had worked, and the act of finding and installing a different browser was something most people had no reason to do. The United States Department of Justice in 1998 decided that Microsoft's bundling of Internet Explorer with Windows was an illegal use of its monopoly in operating systems to gain an advantage in the separate market for browsers. The Justice Department filed an antitrust lawsuit against Microsoft. The lawsuit took several years. In 2000, a federal judge ruled that Microsoft had violated antitrust law and ordered that the company be broken into two pieces, one for the operating system business and one for the application business. The order was reversed on appeal. A settlement was reached in 2001 in which Microsoft agreed to various restrictions on its business practices but was not broken up. By the time the case was settled, Netscape Navigator had essentially disappeared from the market. But the browser market did not stay with Microsoft either. In the early 2000s, a group of former Netscape engineers who had been kept on by AOL but were frustrated with the slow pace of development started an open-source project to build a new browser. The project produced in 2004 a browser called Firefox, which became popular among technically inclined users. A few years later, in 2008, the search company Google released its own browser called Chrome, which over the course of the following decade became by far the most widely used browser in the world. The story of the browser market, from the early days of Mosaic through the rise of Chrome, is a long one and is not really the story of how the Internet works. It is the story of which company makes the software you happen to be using to access the Internet. The underlying protocols that the browser uses, the HTTP that fetches pages and the HTML that describes them, are the same protocols Tim Berners-Lee invented in 1989. The browser is, in some sense, just an interpreter for the documents the network delivers. Whatever browser you use, the documents themselves and the network that delivers them work the same way. There is one thing the browsers did, though, that is worth mentioning, because it has shaped how the web works ever since. The browsers, starting in the mid-90s, added the ability for web pages to run small programs inside them. These small programs, originally written in a language called JavaScript that Netscape introduced in 1995, allowed a web page to do things that were more interactive than just sitting there as text and images. The page could check what you typed into a form. The page could change its appearance when you clicked on something. The page could fetch additional information from the server without reloading. Over the years, JavaScript grew enormously in capability, until, by the 2010s, it was capable of running entire applications inside a browser. The line between a web page and an application gradually blurred. The web today, as you experience it, is a strange mixture of documents and programs, with most pages somewhere in the middle. This is why, when you visit a website now, what arrives at your browser is not just text and images. It is also usually a substantial amount of program code that runs inside the browser to make the page work. The simple system Berners-Lee designed has grown, over the decades, into a much more complicated thing, although the underlying protocols are still the same. HTTP, HTML, and URLs are still the foundations of it all. Everything else is built on top. Chapter 9, The Secret, you can share publicly. There is one more piece of the Internet's design that is worth understanding, because without it, almost none of the things we now use the Internet for would be possible. The piece is encryption. The reason it matters is that when packets travel across the Internet, they pass through many different networks, owned by many different organizations. And any of those networks could, in principle, read the contents of the packets as they pass through. If you were sending your bank password across the Internet in plain text, anyone with access to any of the networks your packet passed through could read your password. Anyone with control over a router along the way could intercept your messages, change them, or impersonate you to the bank. The fact that the Internet works for things like banking and shopping and private messages depends on something that solves this problem. The thing that solves it is a mathematical technique called public key cryptography. And the story of how it was invented is one of the more surprising stories in the history of the Internet. For most of human history, the basic problem of secret communication had a single solution. If you wanted to send a secret message, you and the recipient had to share a secret key in advance. The key was used to scramble the message at the sending end and to unscramble it at the receiving end. The system worked, but it had a fundamental problem. The key had to be shared between the two parties before any secret messages could be sent. If they had never met and could only communicate over an insecure channel, they could never establish a shared key without somebody who was listening also getting the key. This problem was, for centuries, considered to be essentially insoluble. Secret communication was the domain of people who could meet in person, or who could afford to send couriers with sealed envelopes. For ordinary communication over open channels, secrecy was impossible. In 1976, two researchers in California working at Stanford published a paper that quietly changed all of this. Their names were Whitfield Diffie and Martin Hellman. Diffie was 31 years old, with long hair and a beard, and had spent the previous several years drifting around the country thinking about cryptography on his own time. Hellman was a young Stanford professor who had met Diffie when Diffie had walked into his office, uninvited, and announced that he was interested in cryptography. The two of them had been collaborating off and on for a few years. What Diffie and Hellman proposed in their 1976 paper was a mathematical method by which two parties who had never met, and who could only communicate over an insecure channel, could nevertheless agree on a shared secret. The method worked in essence like this. Each party started with a number which they kept private to themselves. Each party computed, using a particular mathematical formula, another number, which they sent to the other party over the insecure channel. The other party combined the received number with their own private number using the same formula, and ended up with a new number. By the properties of the mathematics involved, both parties ended up with the same new number, which they could then use as their shared secret. Anyone listening to the conversation would have heard only the two numbers that were sent openly, and would not be able to derive the shared secret from those two numbers alone, because the math involved was difficult to reverse. The mathematics that made this work involves a kind of operation called modular exponentiation, which is easy to perform in one direction, but extremely difficult to perform in the reverse direction. Multiplying two large prime numbers together is easy. Taking the result and figuring out which two prime numbers were originally multiplied is, with the largest practical numbers, almost impossibly difficult. Diffie and Hellman's method used this asymmetry to make secrets shareable in public. A year after the Diffie-Hellman paper, 3 researchers at MIT named Ronald Rivest, Adi Shamir, and Leonard Adelman published a related technique called RISA, after the first letters of their last names. RISA went further than Diffie-Hellman. It allowed not only the establishment of shared secrets, but the actual encryption and decryption of messages using a particular kind of key that had two parts, called a public key and a private key. The public key could be shared with anyone in the world. The private key was kept secret by its owner. Anything encrypted with a public key could only be decrypted with a matching private key. The system was called public key cryptography, because the encrypting key was public. What this meant, in practical terms, is the following. Anyone in the world could send a secret message to a particular recipient by encrypting the message with the recipient's public key. Only the recipient, with their private key, could decrypt it. The recipient could publish their public key on a billboard, or in a phone book, or on the internet, without compromising the security of their private communications. Anyone who wanted to send them a secret message could just look up the public key and use it. The system also worked in the other direction, for proving identity. If you had a message and you encrypted it with your private key, anyone in the world could decrypt it using your public key. The fact that the message decrypted properly with your public key was proof that you, and only you, had encrypted because you were the only one with the private key. This is called a digital signature, and it is how the Internet now verifies that a message actually came from the person it claims to be from. The combination of these two capabilities, secret communication and identity verification, turned out to be enough to build all of the secure communication that the Internet now relies on. The most familiar piece of this, to most users, is the small lock icon that appears in your browser's address bar when you visit a website. The lock indicates that your browser and the website are communicating using a protocol called HTTPS, which stands for Hypertext Transfer Protocol Secure. HTTPS is essentially ordinary HTTP wrapped in a layer of encryption that uses Diffie-Hellman to establish a shared secret, and then uses that secret to encrypt all of the actual traffic between your browser and the server. When you visit, say, your bank's website, your browser and the bank's server first perform a small dance, called a handshake. The bank presents your browser with what is called a certificate, which is a public key signed by a trusted authority that vouches for the fact that the public key really does belong to your browser. Verifies the certificate by checking the signature against a list of trusted authorities that comes built into the browser. If the certificate is valid, your browser and the bank's server agree, using Diffie-Hellman, on a shared secret. From then on, everything they send to each other is encrypted with that shared secret. Anyone watching the conversation, anywhere on the route between your computer and the bank sees only encrypted gibberish. The actual contents of the conversation are visible only to the two endpoints. This whole system is held together by the list of trusted authorities, called certificate authorities, that vouch for who owns which public key. There are a few hundred certificate authorities in the world, operated by various companies and organizations. They issue certificates to website operators after verifying that the operator actually owns the website they are claiming to own. The list of certificate authorities is maintained more or less by the browser vendors who decide which authorities to trust. This is, in some sense, the most centralized part of the otherwise decentralized Internet. Because if a certificate authority is compromised or behaves badly, the security of many websites can be affected at once. The mathematics that Diffie and Hellman wrote down in 1976, and that Rivest, Shamir, and Adelman extended in 1977, is now embedded into essentially every secure connection on the Internet. Every time you log into a website, every time you make a purchase, every time you check your bank account, the same mathematics is being performed. The fact that this mathematics works, and that it can be done quickly enough on ordinary computers to be invisible to the user, is the reason the modern Internet is usable for anything more sensitive than reading public news articles. The whole apparatus of online commerce, online banking, private messaging, and remote work depends on this small handful of paper, published almost 50 years ago by a few researchers in California and Massachusetts who had been thinking about how to make secrets shareable in public. There is a small footnote to this story that is worth telling, because it is the kind of footnote that turns up only once in a generation in the history of science. It concerns three men who worked at a British government laboratory called the Government Communications Headquarters, or GCQ, which was the United Kingdom's Signals Intelligence Agency. GCQ was, in the 1970s, what the National Security Agency was for the United States. It listened to other countries' communications, it broke other countries' codes, and it employed, in a quiet building in Cheltenham, England, a small staff of mathematicians who worked on the theoretical foundations of cryptography. In 1960, a GCQ mathematician named James Ellis had been asked to think about whether the problem of sharing keys over insecure channels might have a solution. Ellis was an eccentric and self-taught researcher who had joined GCQ after the Second World War, and who had a habit of working on problems that nobody else thought were soluble. He spent several years on the key-sharing problem. In a paper he wrote internally at GKCQ in 1970, he laid out the basic concept of what we now call public key cryptography. He did not, however, find a specific mathematical method to actually implement it. He had described a building, in essence, without finding the materials to build it. The materials were found, 3 years later, by a young researcher named Clifford Cox, who had just joined GCQ from Cambridge. Cox was 22 years old. He had heard Ellis's idea described to him over lunch on his first day at GCQ, and that evening, in his flat, he had worked out a mathematical method that implemented it. The method he worked out was, by every meaningful measure, identical to the Yersa algorithm that Rivest, Shamir, and Adelman would publish 4 years later. Cox's notes, written up and filed internally at GCQ, sat in a classified archive for the next 24 years. A year after Cox, in 1974, Another GCQ researcher named Malcolm Williamson worked out the mathematical method that would later be published by Diffie and Hellman. That work, too, was filed away in the classified archive. The British government, in other words, had invented public key cryptography several years before any of the American researchers and had kept the invention secret because they considered it militarily useful. Ellis, Cox, and Williamson were not allowed to publish their work. They were not allowed to discuss it with anyone outside Q. They watched, through the late 70s and the early 80s, as Diffie, Hellman, Rivest, Shamir, and Adelman published the same ideas and became celebrated for them. They could not even tell their own families what they had done. The fact of their work was finally declassified by the British government in 1997. Ellis had died of a long illness a few weeks before the announcement. Cox and Williamson lived to see their work acknowledged, although they had spent most of their careers unable to speak of it. The story is, in some ways, a quiet tragedy of priority. In other ways, it is a confirmation of how mathematics tends to work. The same ideas had been arrived at independently by two different groups of people working with the same materials. Whitfield Diffie, when he learned about the GCQ work in the 1990s, made a point of crediting Ellis and Cox and Williamson whenever he gave talks about the history of his field. He did not feel that his own work was diminished by the discovery that someone else had gotten there first. He felt, instead, that the work he and Hellman had done had been the work that put the ideas into the world, where they could be used by everyone, rather than locked in a classified archive in Gloucestershire. Chapter 10: What happens when you type an address? We have, by now, walked through most of the major pieces of how the Internet works. The packets, the addresses, the routing, the names and the phone book, the physical wires, the autonomous systems and their slow consensus, the web and the browsers, the encryption that protects the connections. Each of these pieces was invented by someone, in some place, at some time, for some specific reason. Together, they make up the system you use, without thinking about every day. To make the picture complete, it helps to walk through what actually happens, end to end, when you do something simple on the Internet. Let's say you open a browser, type a website's name into the address bar, and press the return key. From your perspective, almost nothing visible happens, except that, after a moment, the website appears on your screen. From the Internet's perspective, the following sequence of events has taken place in something like 1/10 of a second. The first thing your browser does is take the name you typed and translate it into a number. To do this, it consults the domain name system. It asks your local DNS resolver, which is usually a server operated by your Internet service provider, what number corresponds to the name you typed. The resolver may have the answer cached from a recent previous lookup. If it does, it returns the number immediately. If it doesn't, it starts a hierarchical query. It asks a root server which DNS server is responsible for the top-level domain. It asks that server which DNS server is responsible for the second-level name. It asks that server for the final number. The answer comes back, traveling up the chain of intermediate resolvers, and finally arrives at your browser. The whole DNS lookup typically takes between 20 and 100 milliseconds, which is a fraction of a second. Your browser now has the number, the IP address of the server. It needs to establish a connection to that server. To do this, it uses the Transmission Control Protocol, the part of Surf and Con's design that handles reliability. The browser sends a small packet to the server that says, in effect, I would like to start a conversation with you. This packet is called a SYN packet, for synchronize. The server receives it and sends back another small packet that says, yes, I am ready to talk. This is called a SYN-ACK packet. Your browser sends one more small packet acknowledging the response. This three-way exchange is called the TCP handshake, and it takes another fraction of a second. A connection now exists between your browser and the server. The connection is, in a sense, an illusion, because there are no actual wires that have been reserved for this particular conversation. Instead, the two ends have agreed to label all of the packets they will send each other as belonging to this particular conversation, so that they can sort them out from the millions of other packets that are flowing through the network at the same time. The connection is identified by a combination of the two IP addresses and two port numbers, where the port numbers are small additional identifiers that distinguish between different conversations on the same machines. If the website uses HTTPS, which most websites now do, the next thing that happens is the encryption handshake. Your browser and the server perform the Diffie-Hellman key exchange we talked about earlier, agreeing on a shared secret that will be used to encrypt everything that follows. The server sends its certificate, signed by a certificate authority your browser trusts. Your browser verifies the certificate. Both sides derive their shared secret. The encrypted channel is now established. This entire process takes another fraction of a second. Your browser now sends the actual HTTP request, the message that says, please give me this particular page. The request is small, just a few hundred bytes of text, but it is broken into packets by TCP, encrypted by the HTTPS layer and sent across the network. The packets travel through your home router, through your internet service provider's network, through one or more long-distance networks, possibly through an undersea cable if the server is on another continent, and finally arrive at the server's network. The autonomous systems along the way forwarded each packet according to their routing tables, choosing the best path at each hop, using the information they had received through BGP from their neighbors. The server receives the request. The server reads it, figures out which page you wanted, and prepares the response. The response is the HTML document, the program code, the images, and whatever other resources the page consists of. For a typical website, the total response might be a few hundred kilobytes, which is a few 100,000 bytes, which is far too large to fit in a single packet. The server breaks the response into many packets, numbers them in order, and sends them back across the network to your browser. The packets travel back through the same chain of routers, in reverse, although possibly along different paths. They arrive at your computer in some order, possibly not the order in which they were sent. TCP sorts them. If any are missing, TCP asks the server to resend them. Eventually, your browser has the complete response. The browser now begins to interpret what it has received. The HTML document describes the structure of the page. The browser parses it, builds an internal representation of the page and starts to display it on your screen. As the browser reads the HTML, it discovers references to other things the page needs, such as images, fonts, and additional pieces of program code. For each of these, the browser performs a similar process, sending another HTTP request, possibly to the same server or possibly to other servers, and waiting for the response. A modern web page might involve 50 or 100 such additional requests, all happening in parallel, each one going through some of the same steps as the original. Once enough of the page's resources have been loaded, the browser displays the page. From your perspective, the page has simply appeared. From the Internet's perspective, somewhere on the order of 1,000 individual packets have traveled across the world, in roughly a tenth of a second, through a chain of routers and switches and cables and undersea fibers, mediated by protocols that were designed in the 70s and 80s by a handful of people in California and Switzerland and Massachusetts. Encrypted by mathematics that was published in 1976 by 2 researchers at Stanford, named according to a system designed in 1983 by a man at the University of Southern California, and routed by a protocol that depends on the slow, honest cooperation of tens of thousands of network operators around the world who have mostly never met each other. That is more or less what happens when you go to a website. It happens every time. It works almost every time. The fact that it works is in some real sense one of the more remarkable engineering accomplishments in human history. The fact that it works at the scale it does, with billions of users and trillions of requests per day, is more remarkable still. The fact that nobody in particular is in charge of making it work, and that it works anyway through the cooperation of strangers and the protocols those strangers agreed on decades ago, is perhaps the most remarkable thing of all. Closing. If you have stayed with this story from the beginning, and if you haven't, that's exactly as it was meant to be, you may have noticed something about the way the Internet was built. It was built mostly by small numbers of people. A man at Rand who wanted to solve a problem about nuclear war. A graduate student at Ookla who typed the letters low before the system crashed. 2 friends sketching protocols in hotel rooms. A graduate student in California who designed the way names would be organized. A British physicist at a Swiss laboratory who wrote a memo titled Vague but Exciting. A small group of young researchers in Illinois who built a browser that could display photographs. 2 researchers at Stanford who figured out how to share secrets in public. Each of these people, in turn, built a small piece of the larger thing, often without much sense of what the larger thing would become. The pieces fit together, in retrospect, in a way that none of the people involved had planned in advance. Paul Barron did not know, in 1962, that he was designing the system that would carry your video calls in 2025. Tim Berners-Lee did not know, in 1989, that he was designing the foundation of a global system of commerce and culture. Whitfield Diffie did not know, in 1976, that the mathematics he had worked out with Martin Hellman would later make it safe for a person in Indonesia to buy a book from a company in Seattle. Each of them was just trying to solve the specific problem in front of them. The fact that those solutions stacked on top of each other across half a century would add up to the largest cooperative system human beings have ever built was not something any of them quite anticipated. The system, when you look at it carefully, has a particular shape. It has no center. It has no boss. There is no king of the Internet. There is no committee that approves what happens. There are international bodies like the Internet Engineering Task Force that publish standards and recommendations. But the standards are followed because everyone agrees they should be, not because there is a police force that enforces them. The Internet's coordination is almost entirely a coordination of equals, who cooperate because cooperation works better than the alternatives. This is, when you sit with it for a while, an unusual thing. Most of the large systems that human beings have built have centers. The phone network had centers. The banking system has centers. National governments have centers. Markets have, in various ways, centers. The Internet does not. The Internet works because the rules are simple enough and the protocols are documented thoroughly enough that any sufficiently competent network operator anywhere in the world can connect to it and participate. There is no permission to ask. There is no gatekeeper to satisfy. There is just the network, the published rules, and the willingness of the existing operators to forward your packets in exchange for you forwarding theirs. What you have, when you use the Internet, is a system that runs on the small, ongoing kindness of strangers. Your packets are forwarded by people who don't know you. The DNS query that translates a name into a number passes through servers operated by people you will never meet. The undersea cable that carries your video call to the other continent was laid by a ship crew decades ago, who had no idea you would be talking to your friend through it tonight. The browser you are using to read this is built on standards that were written by committees of engineers from companies that have never had anything to do with you. The whole apparatus is held together by a kind of slow, quiet, distributed goodwill that almost nobody who uses it stops to notice. You don't need to remember any of this. You especially don't need to feel that you should have known it before. Most people don't know it. Most people use the Internet every day without ever asking how it works, and that is fine, because the Internet is designed to be usable without being understood. The protocols are designed to hide their own complexity. The whole system is designed so that you can type a name into a bar at the top of a screen and not have to think about what happened. But if you have stayed with the story, or if you remember any fragments of it in the morning, you will know, in some small way, more than you did when the night began. You will know that there are no fundamental mysteries here. You will know that the Internet is a collection of agreements between people about how machines should talk to each other, and that the agreements are simple, and that the machines do as they're told. You will know that behind every web page you load, there is a chain of decisions that other people made, in particular years for particular reasons, and that those decisions are written down in public documents that anyone in the world can read. You will know that when you watch a video tonight, somewhere a packet is being forwarded through a router in a building you have never heard of, by a piece of software written by someone you will never meet, according to rules that were agreed upon by a committee in the 1980s. You will know that the same is true for every other packet in every other conversation, anywhere at the same moment. There is, when you sit with this for a while, a particular kind of strange beauty in it. Most things human beings have built were built by people who could see what they were building. A house has visible walls, a bridge has visible cables, a city has visible streets. The internet is the opposite of this. It is enormous, more than 5 billion users now, more cables than anyone has counted. More devices than there are people, and almost none of it can be seen by the people who use it. It happens in cables buried under streets. It happens in glass fibers at the bottom of oceans. It happens in routers in concrete buildings in cities you have never visited. It happens in the empty milliseconds between the moment you press a key and the moment something appears on your screen. The whole thing, in its visible form, fits in the small rectangle in your hand. The rest is hidden, by design, so that you don't have to think about it. Tonight, briefly, we have thought about it. The room you are in is quiet now. The lights, if you left them on, can stay on or turn off. The blanket, if you pulled it up, is still where you left it. The phone or the screen you are listening through is connected, right at this moment, to the same global system we have just spent the last few hours walking through. The connection is, even now, doing its quiet work. Packets are arriving, packets are leaving. Routers in other countries are forwarding them on. The system is humming, the way it always hums, just out of sight. The story will still be here in the morning. Nothing in the rest of the world is asking anything of you right now. Sleep well.